Hello, hey, welcome here. We are going to do the standing wave lab today. So if you haven't got a chance, get that PDF out that you've been doing all the labs with, number 51. And just to remind you, the last two labs we did, those were ones that I had videotaped back in spring. Hopefully they went well for you. They seem like usable ones. I probably weren't as good quality. I know like that first one was out of focus as we did our first one. And that second one, the sound went out from minute 57 to minute 58. So that's why I sent that email last night giving you that last measurement for the time. It was 20. Oh, I better not say, because I could be remembering wrong, but I think I remember it was 25.09. So that was the timing for the 10 swings on that pendulum that was 150 centimeters long. And that was the only thing that cut out, and then it came back on. So that was good. We just had a little mistake there with the sound. But now I'm back to recording new ones here for the summer. And so again, page 51 kind of describes what's going on. I'm going to have you go forward to page 53. In fact, I'll pull out 53 here and start to draw the table here on the board. The first one, maybe I should put it here. The first row says what is the tension slash mass. Now let me pause right there and fill in some numbers and kind of explain standing waves again. I know I did it in the lecture, so I won't spend too much time here in the lab talking about it. But enough time that you kind of know what we're looking for when we make our measurements. And so going back to our standing wave pattern, maybe at one moment in time a string looks like this, and I'll say string because that's what we're going to do first. We're going to work with waves on a string. Of course, the next moment it switches, and it keeps doing that over and over again. And so as you saw me draw in the lecture many times, there's these magical points called these nodes. And the parts that move a lot, which would be this part, although it would then go down to that part, so I don't really know how to draw that. And so this would be referred to as an antinode. And a big thing I want to remind you as we get started with the lab is that one hump right here, so from node to node, is not a wavelength. It is a half a wavelength. And so what we are asked to do here in this table is to take a string, and maybe I'll draw the picture right under here. And so we take a string and we have a little oscillator. And this is going to make the waves on our string. And the tension would be determined by how much mass we hang. And that's why this first column here in the table is saying, all right, what is your tension and what is your mass? And so part one of today's experiment on the standing waves is to go ahead and look at the standing waves when you have a small amount of tension. So that's where we'll start here with 10 grams. And then increase that, and we'll go to 40 and 90 and 160 and 250. By the way, do you see a pattern in those numbers? I mean, let me help you with some of the discussion questions. But I hope you can see this would be a 1 squared, and then of course times 10. This is a 2 squared times 10. This is a 3 squared times 10. This is a 4 squared times 10. And finally 5 squared times 10. So if you didn't notice that this is a pattern of squares, let me point it out. Because you are needing to recognize that as you get into the discussion questions and try to answer these carefully. And I'll help you with some of these discussion questions. And this is my first bit of help because some of you may not have seen that pattern for me. All right, well, there's a bunch of interesting patterns. And so what we are going to do, if you kind of look here on the table, is the next column says, what is the distance, and I'll just abbreviate, between nodes. And as I was just saying then, the distance between nodes, right over here, nodes to node, is really a half wavelength. So in a moment when I get started and we do the lab together, so again, we're partners, I make the measurements, you start writing down your data, you are going to see me measure from the top of this pulley out to this first node, that first hump. And that first hump then is what I would write down right here. What is the distance between the nodes? And that's as much as I will do for the lab. But where you need to do some work is then the next line. The next line says then, and I'll abbreviate with the lambda, what is the wavelength? And I'll help you here. Hopefully it's really simple, so I'll say it again. The distance right between nodes is half a wavelength. So if we're going to go to here, you just multiply by 2. Now, the next line says what is the frequency. And so when I show you the equipment here in a second, you'll see that I'm plugging it into the wall, and the frequency is set by the current in North America, which is set at 60 hertz. And that you may or may not know, but I'm just going to tell you right up, the frequency is 60. And so I'm going to fill that in and kind of encourage you to fill that in right now. We know that. Because what we ultimately want to see here is what is the speed of these waves. And so using the equation from class, that the wavelength times the frequency. See, that's why it's important you know the frequency and the wavelength. And of course you get the wavelength by doubling this node to node distance we're about to measure. And so when you double that, when you double this to get the wavelength, then you multiply these two together, you're going to get your velocity. And then so I'll just put an X right here because this is not the part I'm going to do. I'm just going to fill in this row right here. But you are getting this row, and then hopefully what you will see is a very similar pattern that we kind of saw in class for the oscillations, and that is if you make it stiffer and stiffer and stiffer, it goes faster and faster and faster. It snaps back. So this number hopefully is getting bigger and bigger and bigger. But here's the ultimate questions for this. And I will look at the discussion questions. The first 1, 2, 3, 4, and then ultimately 5 questions are from right here, part 1. There is a part 2, and I'll talk about that soon. But they say go ahead and compare the speed between this one and this one. Now remember, this is 4 times more. See? Compare the speed between this one and this one. Remember, this is 9 times more. Right? And these are all your square numbers. Compare the speed between that one and this one. Well, that's 4 squared. And then compare the speed between that one. And you will see a pattern down here. Now I will tell you, the pattern here is different than the pattern here. But there is a connection. And that's what they want you to see. And so that's the final thing. They kind of help you with those 4 as you compare 1, 2, 3, and 4. And so you're comparing those speeds. And then hopefully you can answer then this last one. Then how would you describe this pattern? How would you describe this mathematical relationship? And at the risk of giving too much away here at the beginning, let me remind you that we had 2 wonderful equations for the period. A spring, it was m over k. For the pendulum, it was L over G. Both of them had a square root in it, so be on the eye and be looking out for squares and square roots. And so I think that will kind of help you find the pattern. Not a surprise with that square root. And as I said in class, I didn't actually derive the square root for you in class because of the calculus involved, but I will in Physics 123, which many of you will be taking next spring. So more of that to come, but we could at least see the pattern. And I did want you to see that it's not a surprising pattern once you realize that this square root shows up in our mathematics here. All right, well, there is a part 2, and I will talk about part 2 after I do part 1 here. So let's do part 1 here together, and let's fill in this table. So down in front here, I have, and so here's a little oscillator. Here's the string. The string comes along, and so you can see it a little better. I kind of put a black background here on the white string, and then it comes over this pulley. Let me just check the alignment. And right now I have 10 grams hanging from it. And so that's our first measurement here. So I'm going to come over here and turn on the oscillator. If you can kind of see the wires come from the oscillator and they come down to this switch. So I'll just turn on the switch. And so this is going up and down. And maybe you can even kind of see it kind of bounce there. That's the 60 times per second. So I would say I am making at a frequency of 60. And like I said, for this particular experiment, I can't change that because it's plugged into the wall. And I say this particular one because in part 2, we will be able to change the frequency, but not for this one. So the frequency is all 60. What I just need to do is then set up the pattern and make the measurements. So I had already set it up to work really well for the 10, and so I just turned it on, and it hopefully looks really well. Let me take my first measurement, and so as I said, from about the top of the pulley here to the first node, and so there's the first node. That would be the node-to-node distance. And this one's kind of a short one, so I think I can do it with this ruler here. And so I'm going to call that 20.2. And so over here, I will put 20.2 centimeters. Let me just check if I need meters or centimeters. And they don't say, and I think that's okay. I think we'll be better off with meters because later on we're going to do the speed of sound. Although that's in centimeters. I'll do centimeters. What the heck? Okay? So I'll do centimeters. So this is 20.2 centimeters. Now let me change it. So the next one says a tension of 40. All right. So I got a couple weights over here. Let me grab a stack of 3 10s because this little plastic piece on here was already 10. So if I put 30 on here, I'll change the tension. You might have been able to see the pattern change. I could tune it a little bit, but it doesn't look like I need to. It looks like I could still see the pattern really well from the top here to the first node. This is a little bit longer, so let me grab the meter stick for this one. And let me try to do a good job of this measurement. And so maybe a 42. And so I'll call it a 42.0. And so, all right, 40. To 0 centimeters. Now let me go to the 90. Now the 90's pretty high, so I'm going to do a different hanger. Let me take that one off. Go to the bigger hanger. This is 50 grams. And so if I put a 20 and a 20 on here, and that should give me a total of 90. And as we put more tension on it, we might have to make a few adjustments so we can see it a little better. I think that's stable enough that I can kind of see the node hiding right about there. And so let me come over here. And we should probably get a hanger for our meter stick, so we'll have to keep adjusting it here. But what am I looking at? Maybe about a 62, what do you want to call that? 60, no. It's kind of in the middle of where all that is. Maybe a 63.4. All right, so I'll call it a 63.4. 63.4 centimeters. All right, let's go up to the 160. The hanger itself is 50, so if I grab a 100 and a 10, with that 50, make a total of 160. Oh, good, that one came out really well here. It's kind of way over here. It might actually be more than a meter, so I might have to switch to the longer meter stick. No, not quite. Okay. So, let's see if I can kind of hold it there and put the node at 86.2. So I'll call it 86.2 centimeters. And then finally, my last measurement for part 1 is 250 grams. So let me just grab a 200 and put it on the hanger, which is 50. So there's 250. And sometimes it pulls this forward. Got some weights for that, but it looks like that's pretty good. Let's see if I can get a little more vibrations going here so I can see it a little better. I think. Yeah, I'm thinking that might be really good right there. And I'm pretty sure that's more than a meter, yeah. So let me jump over here to the 2 meter stick and see if I can get that to align really well over there. Okay. And if I look down, is that about 105? Boy, I lost my black background. I miss it. Let me get this out of the way. Okay, now. But I think it was around 106. Although maybe, yeah, I'll just call it 106.0. And so somewhere close to 106, and we should probably, like I said, get a nice little mount for that so you don't have to try to hold both ends of it and get it straight, or at least have a partner to work with. Well, in any case, let me pause right there. I'll turn this off and I'll say it again. Here's your job. This is the data from part 1, and so from this, double it to get the wavelength, multiply by 6, get the velocity, and now answer those first 5 questions on page 54, which are looking for the pattern and hopefully you'll see it. If not, shoot me off an email and I'll give you the answer to the pattern.
Units on frequency?
Oh, good. Ron was just telling me that I should probably put the units, which is 60 hertz, so that when you take and multiply down here, you're going to have centimeters per second, because I got centimeters for the wavelength, and then the hertz is the per second. And so we will have units of centimeters per second for each of the speeds. And so I'll let you study that pattern. Meanwhile, let's look at part 2. And so let me clear off the board here and make the table for part 2. If you're looking on page 53 that has the tables, you will see that there's 2 of them, because we're going to really repeat what we just did, except this time we're going to do sound waves instead of the waves on the string. And of course, sound waves you can't see with your eyes, but you can hear with your ears. So it's a little different, but it's the same idea. And sound waves, as we learned, do not change their speed based upon any tension. So there is a little different. So what we're going to do is use one column or one table here, make a bunch of measurements, and get the speed of sound at a particular frequency. And the reason there's a second table is then we're going to then measure the speed of sound at another frequency. And if you remember from class, of course, we didn't say anything about the speed of sound changing with frequency, and because it doesn't. And so that's hopefully what we will see. We will do 750 hertz at first, then we will go to 1500 hertz, and in both of those cases, hopefully we'll get roughly the same speed of sound. And so we'll be able to measure the speed of sound today, and then hopefully convince ourselves that the speed of sound doesn't change with the frequency. So when we go to a different frequency, we will of course get a different wavelength, so the 2 match up. All right, so the table, and they're both of them, they kind of look like this. They say, find the position of the nodes. And so we're going to set up a standing wave pattern. And as you will soon see, there will be 5 nodes. And so your table has listed the number of nodes 1 through 5. And so we're going to find those positions. Now, that's what makes really the difference in doing the sound compared to the string. Because the string, finding the positions of the node wasn't hard. Just use your eyes. There it is. See them, lay out the meter stick, and there they are. But when it comes to the movement of these molecules, we can't see where the molecules aren't moving. But we can still find them nonetheless. Now, I will work with you on this one, but then, and I shouldn't have made these lines all the way down. Once you know where those nodes are, it's going to be fairly easy, I hope, to find the distance between the nodes. Because this is why your box kind of looks like this. Because if you subtract 2 from 1, that would be the distance between the second and the third node. And then if you subtract 3 from 2, that would be the distance between those 2 nodes. And 4 from 3 would be the distance between those 2 nodes. And 5 from 4 would be the distance between those 2 nodes. So that's what you're going to be doing. You're going to be doing the part with your calculator and subtraction and some other calculations. But let me actually then show you the equipment. Let's make these measurements. So come over here to our sound tube, and I'll show you what I mean by its position. This is the sound tube. I've got this long column of tube, but you see it's got a plunger in it. And I can move the plunger back and forth, and essentially I'm changing the length of the plunger here. And so there is this tape on here that, says how far is it from this edge. Well, that's interesting. That's 0.
Oh.
So we have this backwards, but that's okay. We'll just count backwards. So somehow this got switched around here. So I will just, count backwards. And so we'll still take the difference. And so instead of 2 minus 1, maybe we should go 1 minus 2. So we have a positive number here. Anyway, so this right here is actually 100 from here. And then 110 and 120. And it's kind of burnt off on the end, but that's okay. We don't even need to see the end. Because here's how we find the position. We listen with our ears. I'm hoping you can pick this up with the microphone. I did give it a little bit of test, and it seemed to work really well. And so I'm going to start with the plunger really near the speaker. So here's the speaker. I'm going to turn on my equipment and going to recognize, first of all, that this is sending an electronic signal here and making the paper diaphragm on that speaker go back and forth 749 times per second. So remember that. We'll put it in our table. But of course, one of the things we need to get the speed is frequency. We need frequency and we need wavelength. So that's the frequency part of it, 179. 749, yes, thank you. So I got to say it right. So if I pull the plunger out, I'm hoping you heard it got loud right there. I'll go back and forth. And so as I go back and forth, that place where it gets really loud, and I'll just shut it off here and kind of explain. Remember, the plunger's kind of getting in the way. But remember, a node is where the molecules don't want to move. So if I put the plunger right at a node, I'm really not interfering with the wave. If the plunger is anywhere else, it interferes with the wave. So a simple explanation here is when it gets the loudest, I must have the plunger at the node. So I can't see it, but I can still find it by listening with my ears. All right, so I'm looking around for my marker. There it is, and I'll go ahead and then find that first node. Let me just double check that it goes back to the same frequency. Good, 749. And let me just move it kind of back and forth until I think it's the loudest. So I'm thinking that's the loudest. And if I look at the edge of the plunger, and I'll just do centimeters, this is 112.7. So coming over here, I will put 112.7 centimeters. All right, let's find another node, the second one. So I'll kind of listen. So right there sounding pretty loud. So this is 89.4. So 89.4 centimeters is where the second node is. Keep going. So maybe right there is the loudest spot. And so this would be, are these 60, 66? So 66.8. So 66.8. And then let's try the fourth one. Try to get close. Oh, kind of jammed here. So it's somewhere in this area. I think I can still hear it like that. Yeah, it seems to be right there where it gets kind of jammed up. But that looked like the right one. So 43.3. And then finally, the last one maybe right about there. And ooh, let me call it 19.8. I think it's kind of messed up there, but 19.8. And let me turn this off for just a second so I don't have to keep listening too much to it. But here's what you're asked to do then, now that I've collected the data, is of course find the distance between the nodes. So if you subtract those two, you get the difference. Subtract those two, you get the distance. Subtract those two, you get the distance. Subtract those two, you get the distance. And so each of those should be really representing a half wavelength. That's why, like we just did in step 1, once we know that distance from node to node, you can do this line, which is what is the wavelength? And so just double that. Now, the frequency of this whole experiment, as you saw, was the 749 hertz. And so we made all of these measurements at the 749 hertz. So we didn't change the frequency during this first step. We're going to change it now going on to the next step of part 2. But that's the frequency. And then hopefully then what you can do now is fill in this last step, which is what is your measured velocity for the speed of sound. And so take your number for the wavelength, which of course is in centimeters, and then multiply it by your frequency, and you will get a speed in centimeters per second. And if you remember from class, I said in a room setting, and it's a little warm in here, we would get a speed of about 344 meters per second. If I go ahead and say this is centimeters, so that you can see if you're getting close, I hope that your numbers here are somewhere near 34,400 centimeters per second. And so that is that is the speed of sound that's kind of expected in a regular room temperature environment. And that's roughly where we are. It's why then at the bottom of the table, your author says one more thing. He says, really what we've done here, because we've measured the wavelength 4 times, we've really measured the speed 4 times. And like any measurement, some of it may be high and some of it may be low. So take the average of these and write down your average. And your average is probably a better measurement than any one individual measurement, because like I said, there's always some mistake. You know, I might not have heard the position quite right. More like when it was jammed there, maybe I was messing something up. And so one individual measurement is never really that accurate. But now I have 4. And so the average, I'm hopefully, is a real good measurement, I hope. So let's see what you get here. And then you repeat all of this. And so let me go ahead and repeat this for step 2. And I'll go ahead for step 2 by just saying, let me just use the same table. I'll just erase these numbers. And as you will see, we are asked to do it a second time at a different frequency. So let me erase that number. This second table is then asked to do it a frequency at about double the one we had. Okay, so we were roughly 750. Let me come over here and make some adjustment here. I'll turn it back on. And turn up the knob to about 1500. It takes a little while for the oscillator to settle in, so I'll move the plunger in while it's settling up. Looks like I got a 1427. And that's maybe a little on the high side, but that seems like a good place to start. And let's just see if I can kind of hear them. So maybe right there. Oh. Yeah, maybe right there. So let me go back. So maybe one is there. Maybe two is there. Maybe three is there. And four is there. And this is always the challenging one, especially with this speaker. Now I wish I would have grabbed some of our older ones actually work much better, and my bad for grabbing this one. But let's see what we have here. In fact, now that I think about it, I'll just try something here. If I go to a little lower frequency, because we're not doing well with this speaker. Yeah, I think that's a little cleaner. So I'm going to run at this one, which is a little bit lower than half. But 1445 sounds like a good one here. So I'll put this in my table. And so 1445 hertz is going to be our frequency for our second run. And now let's see if we can find those 5 positions. And then you're going to end up doing the same math. So I'll call that the first one. And so 100, 110, 118.2. So the first one is at 118.